Okay, welcome. All. This is another edition of the One World YoungStatS webinar series. It is our 16th webinar in a row. One World YoungStats is a webinar series which started in February 2021 under the role example of One World Probability Seminars. It is part of the YoungStats project taking place in Young Statisticians Europe initiative of the FinStats Association, Federation of European National Statistical Societies. It is supported by the Bernoulli Society for Mathematical Statistics and Probability, as well as the Institute of Mathematical Statistics, and endorsed, I would say, also by the Econometric Society. Today we have pleasure to feature a novel webinar on the topic of recent challenges in model specification testing based on different data structures. Model specification testing is one of the essential methodological tasks in statistics. Recently, with the development of different data structures, envisioning concepts from classical data setups to other environments becomes very important. And today we feature four, I would say, statisticians, younger statisticians, selected by the discussant Bojana Milošević of University of Belgrade, Serbia. I welcome Thomas Berrett from University of Warwick, United Kingdom, who I think has just been recipient, correctly if I'm wrong, of a Bernoulli Award of the Bernoulli Society. We also welcome Julian Gerstenberg of Goethe Universität Frankfurt Institute of Mathematics, Germany. We welcome Marija Cuparić of University of Belgrade, Serbia, and we welcome Charles Pretorius of University of the Free State, Bloemfontein, South Africa. So without further ado, I would give the word to Thomas Berrett to present on hypothesis testing under local differential privacy. Each talk will be about 15 to 20 minutes long. Please insert your questions that anybody in the public has in the chat. We will try to ask them following the presentations or in the later debate. I also know that the webinar is recorded and will be accessible on the YoungStatS YouTube channel later. So Tom, please, the word is yours. Thank you.
Thank you very much, Andrea, for the introduction, and yeah, thanks for the opportunity to speak here. I'm very grateful. So, as Andrea says, I'm going to be speaking about hypothesis testing under local differential privacy. So this is, I'll mention results from 2 or 3 recent papers that I have, and I'll start with a general introduction to what I mean by differential privacy, and in particular, what I mean by local differential privacy. And we'll see how this constraint of differential privacy affects the behavior of testing in classical statistical problems. Okay, so just a brief introduction. I would say that the field of differential privacy has been driven recently by a lot of applications in kind of technological companies. So, for example, some of the logos you see here have implemented private statistical methodology into their products. Now, there have been kind of high-profile cases of data breaches or sometimes unethical data use, and these kinds of situations lead to pressure from regulatory bodies and the public to implement statistical procedures or data collection procedures that can respect individuals' privacy and security while still retaining strong statistical performance. So that's the idea of differential privacy. As I say, it's largely been driven recently by technological applications, but of course there are many classical statistical settings where data that is collected is highly personal or highly sensitive, and it's the kind of thing that you wouldn't necessarily want to be released into the public domain. So I'm thinking about classical statistical areas like medical data or financial data, or even the census. These areas contain lots of information that is sensitive. now the traditional way of dealing with sensitive data is a simple anonymization, where you might remove the names and addresses of the people from your data set. So you might call a data set anonymized if each observation is not labeled according to the individual it comes from. However, there are a few kind of well-known examples that show that simply removing names and addresses is not sufficient in order to truly protect somebody's data. So this is one example I like to mention. So this is when a researcher, Sweeney, in 2002, was able to use an anonymized medical data set to identify certain individuals in that data set. And probably the most high profile of those individuals was the governor of the state of Massachusetts. So what happened was there was an anonymized medical data set that was published that includes these variables you can see in the left circle here. So that includes zip codes, birth dates, and sex. And then what Sweeney did was found another data set which was publicly available. So this is this voter list shown on the right. And crucially, there was an intersection between these two data sets, so that zip code, birth date, and sex were recorded in both data sets. Now, this data set on the right had names and addresses attached, and these three variables here in the middle, in the intersection, were enough to uniquely identify certain individuals in the anonymized medical data set. So I think the point here with this example is that you can't really control what information is out there in the public domain already. And so it's often insufficient to use traditional anonymization techniques. Now, the idea of differential privacy is that the only way to really secure somebody's data is to randomize it, or to add some noise into the data collection or data analysis pipeline. So a kind of cartoon version of this is what's shown here. So you might take a raw data set and you might add some noise to it in order to create a secure data set. Now, with most types of data, there are many different ways that you can add noise, and you can also choose how much noise to add to your data. Differential privacy is one particular way of measuring how much noise is being added to data and how much it is protecting the privacy of the individuals in the data set. But it's a choice. Okay, so the way that researchers in differential privacy choose to measure the amount of information in a data set is with this constraint here. So if Q is our mechanism, so Q is a conditional distribution which tells us how to generate randomized data given an input data set, then Q is said to be alpha differentially private if it satisfies this likelihood ratio condition here. So what this is saying is that if you have two data sets which only differ in a single observation, then the output distributions from your mechanism have to have a bounded likelihood ratio, and that bound has to be no larger than e to the alpha. Alpha here is a parameter which controls how private this mechanism is. So for very small values of alpha, this is a very strict constraint which says that the output from your privacy mechanism can't depend on the input very much at all. On the other hand, a large value of alpha is quite a weak constraint. So this is one way of measuring how much information about individuals is in a privatized data set. And it has become the most popular way of measuring that quantity. So it's really the main constraint that people use when they want to use private statistics. These are some of the applications that have been recorded. As I mentioned earlier, you can see lots of big tech companies here, but this has also been implemented in the US Census, and other researchers have written about how this could be used to demonstrate GDPR compliance. So this is the main way that people use to measure how much information is in a data set about individuals. Now, when this constraint was originally introduced, it was mainly thought of in this top picture here. So this is what I would call the central model of differential privacy. So this constraint allows you to gather all of your data into one place, to analyze it, and then to release some privatized version of your statistics, which we call Z. Now, crucially, what these kind of procedures require is a trusted third party who has access to all of the raw data and is allowed to do what they want with it. The only constraint that differential privacy imposes is that the results of that analysis cannot be directly published. They have to be randomized before they're published. This is sometimes called the central model of differential privacy. Now, what I've worked on is the local model, which is this picture shown in the bottom here. And this imposes a stronger constraint because it says that there is no third party that can be trusted to see the raw data. The raw data is only ever seen by the individual that it relates to. So individual one randomizes their data and then transmits their data to a central server. And similarly, X2 randomizes their data and then submits it to someone. But here we allow some interaction. So we allow the second person's data point to be randomized based on the output of the first person's data. So this is a stricter model, but this is the local model. And crucially, it means that nobody else sees your data apart from you yourself. Okay, so that's a brief introduction to privacy. I'm going to now talk about how these constraints affect rates of convergence or error rates in a couple of well-known statistical problems. So we'll start with simple hypothesis testing, which is, as the name suggests, quite a simple problem to get started with. So let's consider this problem. We've got 2 point hypotheses, and we've got data x1 up to xn. This data has some distribution p, and p is either p0. This should be a p1. So we're trying to decide whether p is equal to p0 or p1. If you had access to the raw data, then it's well known that the optimal thing to do is to use the likelihood ratio statistic. So you take the likelihood ratio statistic between P1 and P0 and take the product over all your data points. And this is known to have optimal error properties. In fact, as it turns out, this statistic is very difficult to privatize. So it's very hard to use something like this under a private model. But what is easier to privatize is something called the Chef-A test, which is an idea from robust statistics. So this is what I've shown in the bottom display here. So this is the test that we're going to start with rather than the likelihood ratio test, because it's going to be easier to inject noise into this procedure. And crucially, you can see here that the effect of each individual data point is really quite limited, because it can only affect this indicator function here. If you compare this to the likelihood ratio statistic, you could see that a single data point in the likelihood ratio statistic could have quite a large effect, whereas in the Chef-A test, it only contributes a 0 or a 1, so it's a relatively small effect. So the Chef-A test works by counting the number of points that lie in a certain set and comparing that to a threshold. And this set is chosen to give us the total variation distance between P0 and P1. Okay, so how do we add noise to this procedure to make it private? Well, actually, this is the very easiest kind of data to privatize. What we've essentially done is we've transformed our data into a binary piece of information, and privatizing binary information is something that people have been doing for a long time, since at least 1965, when Warner introduced the randomized response mechanism. It's a very simple mechanism. So With a certain probability, we keep the binary data the same. And with a certain probability, 1 minus that initial probability, we flip the answer. We can correct this data to give an unbiased estimator of what we want. And so we can define the following test. If the probability is chosen in this way, so to be e to the alpha divided by 1 plus e to the alpha, then this is an alpha differentially private procedure. It's very simple to analyze. This is binary data, so we can use Hoeffding's inequality, and it's easy to calculate the mean of this variable as well. And we can show that the risk of this test is bounded above by this quantity here. So it decays exponentially, and the rate is like n times alpha squared times the squared TV distance. So alpha here is the privacy parameter. Small values of alpha make the problem harder. And this is how the error decays. We can also see that we have a corresponding lower bound, and so this really is kind of the optimal rate. This was known previously, and this is quite simple to do. But what we wanted to do in our work is to really go a bit deeper into the connections with robust statistics. So as I said earlier, the test that we're using is something that comes from robust statistics. And it's been seen in the previous literature that when you consider contaminated models, such as Huber's contamination model, the total variation distance comes into play, whereas in classical statistics, you would expect the Hellinger distance. What we did in our work was to combine a privacy constraint with some contamination and to study the rates of convergence in that problem. So just to briefly run over these rates. So we're considering simple hypothesis testing in a few different models here. In the classical model, it's well known that the Hellinger distance controls the difficulty of this problem. And so you have good error properties if the Hellinger distance is above some threshold, 1 over square root n. It's known just from the robust statistics literature without privacy that if you have contamination, then your total variation distance needs to be above some threshold in order to have power. It's known in privacy without robustness that, again, it's the total variation distance that's important. And what we see is that if you have both of these things, then it's very simple. It's again the total variation distance, and the threshold that it has to be above is the sum of the previous thresholds. So what we're trying to say here is that privacy constraints change the difficulty of the problem in a similar way to the way contamination changes the problem. There's some kind of link here between robustness and privacy. This has been previously studied in the local model in papers as far back as 2009. But in our work, we study this link in the local model for the first time. We also consider some other problems such as mean estimation and median estimation and density estimation, but I'm just going to talk about this hypothesis testing problem here. Okay, so that's kind of how privacy affects rates of convergence for simple hypothesis testing. I know I'm running out of time, so I'll just very quickly go over how it affects a goodness of fit testing problem. So what I mean by goodness of fit testing here is a problem with a simple null hypothesis and a composite alternative hypothesis. So I'm going to assume that we've got discrete data, and I'm going to test the null hypothesis that P, the distribution, is equal to P0 for some fixed P0, versus the alternative that the true distribution is separated from that null. There's been a lot of interesting work on this problem over the last 10 years in classical models, and it's been shown that the difficulty of this problem really depends heavily on the specific null that you want to test. So certain null distributions are easier to test than other null distributions. And very roughly speaking, this is not exactly correct, but something like the 2/3 norm of P0 is controlling the difficulty of this problem. Now, the question that we wanted to answer is, how is this local testing rate affected by the differential privacy constraints? And what kind of methods should we use to translate the optimal test into a private setting? And an interesting point about this problem actually is that it reveals something else about privacy that is interesting. So in the simple hypothesis testing that I just talked about, we saw that a non-interactive method was optimal. So this was a method where data point x1 was turned into a binary piece of information and noise was added to that, and then the noisy versions were analyzed. Actually, in this problem, which is more complicated because there's a composite null, we see that we can significantly improve the rates of convergence if we allow some interaction between the individuals. This doesn't affect the levels of privacy given, but we're just allowing some communication between individuals here. I'll skip over that, but I'm just saying that we're measuring error in a minimax sense. And what we show is that the minimal separation needed in order to have good power can be upper bounded by these quantities here. So if we're measuring distance in L1, then this is the rate of convergence here on the left. And if we're measuring distance in L2, then an upper bound is given here on the right. And in particular, for uniform distributions, the rate is d to the 3/4 here and d to the 1/4 here. And we see actually that if we allow ourselves to use interactive mechanisms, then the rates change. So we get a d to the half and just a constant here instead when we allow interactive mechanisms. So the rates are kind of abstract, but we have some examples here to hopefully help with the interpretation. So the easiest kind of distributions to consider are uniform distributions. In the L1 case with non-interactive mechanisms, the rate is given by this quantity here. So we have a d to the 3/4 in the numerator. With interactive mechanisms, it's d to the 1/2. And you can compare this to the non-private rate where you have d to the 1/4. I'll skip over the mechanism, but what we're doing is we're privatizing a U statistic. We're kind of taking the natural test in the classical setting, which is a U statistic, and adding noise to it. We can also extend this to the continuous case. So I have some rates here when the nulls are continuous, and we test using the L1 distance. Okay, so I'll just very quickly wrap up. So I've considered two different problems here. So simple hypothesis testing and goodness of fit testing, and hopefully I've tried to give you an idea of some of the challenges that local differential privacy brings and how this constraint affects behaviors of optimal tests. You always get a reduction in your effective sample size when you have a privacy constraint, but it can also change the form of the rates. So we've seen that in problems where the Hellinger distance is important in classical models, the total variation distance is important in private models. And with more complicated problems, there can be a difference between non-interactive and sequentially interactive rates. These are the main references. So this most recent one is where we talk about robustness. And in these two older ones, we talk about differences between non-interactive and interactive mechanisms. So thank you very much for listening.
Thank you, Dr. Klepp. Great presentation. Is there any question from the audience? Maybe to stimulate debate, and we can naturally also have a debate afterwards. You are using total variation distance in your analysis. Would any other distance, there are tons of distances used in statistical analysis today, could any other also be appropriate for such analysis?
Potentially. So in the goodness of fit testing, the use of total variation distance was a choice. So we chose to measure separation using the L1 distance chiefly, but we also considered the L2 distance. So it was a bit harder to work with the L2 distance, but it was a choice there to use the L1 distance. In the 2-point testing problem, the TV distance really arises naturally. So it's not something that we chose in that problem. So you can prove this upper and lower bound, which kind of proves that the total variation distance really is the crucial quantity there. So this one was not a choice.
Mm-hmm. Okay, thank you. Thanks a lot. I suggest we go forward, also due to time reasons. Thanks again. And I would give the floor now to Julian Gerstenberg.
Yeah, thank you very much. I make it big. So you can see it now? Yes, great. Okay, thank you very much for the invitation. In my talk, I will talk about exchangeability theory and its application to non-parametric statistics. The goal of the talk is to motivate the research field of data structures and exchangeability theory from a non-parametric statistics point of view. So it will be a very basic themes we talk about. For the basic thing for sequential data is the very basic assumption you often see is you assume your data is x1 to xn in some feature space, and you assume it to be IID with an unknown marginal distribution. So it's a classical setting. And the task there is to make inference about the unknown marginal distribution based on your observations. For example, your estimation problems or hypothesis testing problems or so. Okay, now the talk goes in a direction that we want to consider other data structures and ask similar questions. For example, you could imagine a situation where your data is not in a sequential form, x1 to xn, but comes in the form of an array, an n times n array. So we have observations xi1, i2, and both indices 1 from 1 to n. And n is to something like the sample size. So you could imagine a situation where you sampled n individuals from a large population and measured relational information between individuals. And then the data would be of this n times n array form. And then the first question is what even is now a suitable replacement for IID with marginal distribution? In the sequential case, it's more or less obvious. If you sample individuals from a large population, then you model the data as IID. But if you pick individuals and measure relational information, it's not clear what's a priori clear what's the right notion of IID in this situation. But exchangeability theory gives an answer. You would model this as an exchangeable array with certain properties that will be the topic in the second part of the talk. And then if you have answered the first question, what's the right notion of IID with unknown distribution? In this case, you can do inference based on the data you have. So you could consider estimation problems, hypothesis testing problems or so. Okay, and then the general ideas you will see they do not only apply to array data of this form, but in some sense they apply to arbitrary data structures in some sense. So you can generalize it very broadly, and this will be the third part of the talk. Okay, so in the first part I will recall some basic things about the classical situation about sequential data. So to recall, the basic assumption is often in a one sample problem, you can say the basic assumption is often that you have data x1 to xn. You assume it's IID with an unknown marginal distribution, and marginal distribution is this p. But if you've in this IID assumption, you could think of there's an infinite IID sequence, but you have only observed the first n entries. So potentially you could make more observations. But right now you only have the first n observations. Okay, goal is to make inference about unknown marginal based on observations. And the general themes in this sequential setting is you can estimate the unknown distribution P by the empirical distribution. Okay, and then if you're interested in a specific aspect of the marginal, a function of P, you can estimate it by plugging in the empirical distribution. And it works if this G is suitable, nice, in some sense. For example, if this parameter theta you're interested in is an expectation over a test function, then of course nice estimators by law of large numbers justified empirical mean. Okay, or in this general setting, goodness of fit problems often takes the form. You have a hypothesis P0, your hypothesis is a true distribution is P0. You choose a suitable distance of probability measures and reject if the distance of your empirical distributions is too far away from the hypothesis. This also fits in this general concept. And of course, if you want to analyze things and you have certain theorems available, law of large numbers or uniform law of large numbers, central limit theorems, functional central limit theorems, and U-statistics theory, for example. The U-statistics I will mention because it will very nicely generalize to the very abstract setting. Okay, situation, you have x1 to xn IID with unknown marginal distribution, and maybe you're interested in a parameter that takes the form of an expectation over a kernel function of degree k for, let's say, it's symmetric kernel. And of course, the estimator based on your data is this mean over subsamples of your data. Of course, it's the story is the statistical story behind this is you assume you have picked n individuals from a large population at random, and you're interested in the mean over a subsample only of size k. But if you have a sample of size n and n is larger k, you can estimate by picking subsamples of size k from your data. And this will be the form of the U-statistics. And if you, for example, if you have observed 9, sample size 9, and your degree you're interested in of the kernel is 4, in calculating the value of the U-statistic, you would basically take the mean over all 4 out of 9 choices. So this is a picture you get. Okay. And of course, you have the nice general U-statistic theory. You have consistency as n goes to infinity. You have this asymptotic normality. Maybe it's degenerate, and then the higher order U-statistic theory is also available. Okay, now what's the situation with array data? Okay, maybe you can, from statistical point of view, make the same assumption in the first place. You pick n individuals at random from a large population, and now you measure relational data, and this gets you your n times n array. Okay, and now what's a reasonable replacement for IID in this situation? You can extract it from the idea itself. You would say, okay, if I pick individuals from a large population, I could have picked maybe infinitely many individuals and measure information. So you could say there's an infinite, there should be possible to be an infinite array of random variables like this, but you have only observed a finite subarray. And now if you have this individuals are picked at random from a large population, this infinite array should satisfy the exchangeability property. So if you relabel jointly exchangeable, if you relabel the indices according to bijections, it shouldn't change the distribution because you picked individuals at random. So the name of the individual shouldn't matter. And it should also be dissociated. That means if you have, if you consider for your individuals you have picked two disjoint subgroups and consider, so A and B disjoint subgroups, and consider only the entries of the array where the pairs are restricted to A times A or B times B, these should be independent. But this is this does not mean that all the entries in the array are independent. This would be too strong. For example, if you pick a special individual and it may give dependence on all its variables it belongs to. but the dissociated property is reasonable. So from a statistical point of view in this array setting, you could say, okay, your data comes from an infinite array, which is exchangeable and associated, but besides that, you don't know its law. Okay, what can we do now? Okay, we have two cases. The sequential data case, you have x1 to xn. In this array data case, you have an n times n array as data. In the sequential case, to recall, the goal is make inference about the unknown marginal based on data. And in the array case, you could say make inference about the unknown law of an exchangeable dissociated infinite array. This would be the straightforward thing, but it's strange. What should that mean? Make inference about a law of an exchangeable dissociated infinite array. It's on the same level as saying in the sequential case, make inference about an unknown law of an IID process. But laws of IID process are determined by the one-dimensional marginal, so that's clear what this means. So, but for the array case, it's not so clear. So you could ask, what's a nice parametrization of laws of such infinite arrays? And there, the Aldous-Hoover-Kallenberg theory gives you functional representations. But the functional representations, it's like for every such array, there exists a measurable function, and then you can put in randomization and get an object that has the same distribution. But the problem there is these measurable functions are not unique. And it's the same as in the sequential case. If you have an infinite IID sequence, xi, you can say if the state space is nice, you have a measurable function from the unit interval to the state space, such that your process has the same law as FUI, where you plug in IID uniforms. But of course, it's not from a statistical point. You can parameterize IID laws by these functions f, but it's not unique, so it's a little bit of problem. So the unknown distribution as a whole may be hard to tackle from a statistical point of view here in this array situation. But certain aspects of the distribution, you can tackle it, for example, these U statistics. This works precisely as in the sequential case. So if you have an n times n array observed and you make the statistical assumption, it's a finite subarray of an exchangeable infinite array, x now n. And maybe you're now interested in an aspect of the unknown distribution. That an aspect that comes as a form of a parameter theta, that's an expectation over a test function that takes in small k times k arrays. And now with the same statistical idea, you can estimate it. You have the idea that you sampled n individuals from a large population, and this would be an expectation over only k individuals. So now you sample k of n individuals, and on the array level, this corresponds to inducing small subarrays of size k. So this would give you now this picture. For example, if you have observed a 9 times 9 array, and you're interested in a expectation over a kernel of size 4, you would sample smaller subarrays like this. And then over all such choices, take the mean over the kernel value. And you can prove this works. It's asymptotically, it converges almost surely to the true parameter. And also it's asymptotically normal with order square root of n. But again, of course, the sigma could be 0. So then you would want to look at other asymptotics. And this theorem, I think for the array case, it's known for a long time, but you can use very general theory to prove consistency and asymptotic normality here. For example, consistency you can use from ergodic theory, so pointwise theorem for amenable group actions. You can use that to get consistency. And for asymptotic normality, it was shown that in this very general setting, the almost sure convergences under suitable regularity conditions always asymptotically normal. It was shown recently in this second paper. And you can apply this for this situation and get this result. And also there was a work empirical process result for exchangeable arrays, where in this situation, it was shown that the consistency and the asymptotic normality does not only hold for one fixed test function, but for uniformly over a class of test functions, particular choice. So you get functional central limit theorems. And yes, but it was shown for this array situation, but not only for depth 2 arrays, but for depth k arrays, where you have k indices. Okay, so, and if you have this result about the U statistics, you can use that to make estimation and confidence intervals or hypothesis tests. In principle, you could use this result for this. Okay, now maybe a short outlook in my own research is this type of notion of exchangeability for arrays, it extends to many other types of data structures. Higher order arrays, you have not just relations of depth 2, where you compare 2 individuals, but maybe you compare k individuals. And the idea there was to make a general definition for data structure that can be used, that provides you with the statistical operations of inducing substructure and inducing submeasurements. The abstract definition provides this operation, and that alone allows you to develop a theory of exchangeability and this U statistics, for example. And the abstract definition is it has category theory flavor. It's the abstract definition of data structure would be a rule D that sends every finite set A, for example, the set 1 to n, to a nice measurable space dA. You think of that as the space of possible measurements on a finite group of n individuals. And then you have this operation of inducing substructure. For each injection tau B to A, injection corresponds to picking a subgroup from a larger group. You get an associated map that allows you to extract the subdata from your measurement. So if you select a subgroup A and call the individuals B according to such tau, and you have measured information on the larger group A, then d tau maps the measurement to the subgroup. And it should allow, it should satisfy the functor properties. And in the category theory notion, you would call such an object a contravariant functor between suitable categories. And of course, the sequential data and the array data is included in this general framework. For example, sequential data, the dA is just functions from A to X, from indices to features. And d tau extracts from a sequence a subsequence. Or with array data, your measurements on the finite group, let's say A is 1 to n, is n times n arrays over a feature space X. And extracting submeasurements according to an injection works like applying tau like this. And this definition is very general. Very many examples of exchangeability in data structures are covered by this framework. So from a statistical perspective, you can use it like this. So maybe your observation on a sample of sample size n, you could call it xn. You say, okay, maybe it takes values in a space dn, where d is this abstract data structure. And the frequentist statistical assumption would be your xn comes from something that is an exchangeable dissociated with unknown law. And if you think about the statistical idea in mind, you pick individuals at random and measure information now on every finite subgroup, then your assumption would be this xn, your observation comes from a process xn that satisfies sampling consistency, exchangeability, and an independence property. And you can use this this mechanism of this provided by the data structure, this inducing submeasurements, to formalize it with that. So you have this abstract concept of data structure, which gives you an abstract concept of IID with unknown marginal distribution in some sense. And then you have the story again. Maybe you are now interested. You are on this point. You have your observed data is like this, and maybe you say now I don't know the concrete law it has, but I'm interested in a parameter theta that comes as an expectation over a test function. Now the test function takes in measurements on a size k group. And again, you can define a U statistic in this abstract setting. And you can use the theorems, this ergodic theorem and the asymptotic normality theorem, the works, to prove here also consistency and asymptotic normality in this abstract setting. Yes, and final remarks. Like for the array case, you cannot, of course, it's more general. You cannot make a injective parametrization of these IID laws, but you can use Hoover-Kallenbach theorem to give a functional representation again, also in this abstract setting. But now in this very abstract setting, because you're somehow in this category theory world, you would use notions like natural transformation to make functional representations. And I think there's much to do in this direction, because many of this classical statistical theory for sequential data, like empirical process theory, or yes, this also other aspects of this U statistics theory, you could ask it very similar for the general case and ask what theorems hold, how do they look like. And okay, you can use the classical setting. It was a one sample setting I explained now. You have this one group where you pick individuals from. You could also ask, how does it look like for M sample problems? That you could make the same ideas, this category ideas, to formalize it for M sample problems. And the last, the way I got interested in it was because I worked as a programmer for some time, and always worked with these software packages that implement the empirical risk minimization principles, like scikit-learn and so, for this Python package. And I think this abstract point of view would also, it's also a nice thing if you ask yourself, how would you build the interface of software packages that extend these empirical risk minimization approaches to more than sequential data, to relational data. Okay, that was it. Thank you very much for the...
Excellent. Thank you. Thanks a lot. Also, there will be a lot of questions. I'm checking the chat. Just one short, hopefully, from Žikica Lukic. Could we look into arrays which are m times n arrays, where m is a function of n, say m is equals to n, and not n times n arrays? Could the array data case be generalized? This would be the question I would also have, to matrix and or tensor data without using abstract concepts like category theory, which you used.
Okay. The n times m array in the sense of a two-sample problem, or what's the idea of the m? The question is, what's the interpretation of the m?
The array, maybe Žikica, if you unmute.
Yeah, so basically you looked into the matrix, which is n times n, starting to work with the array data. And my question is related to the case where we start with the data, which is not a square matrix. We look at m times n matrices. So you said we have like n people and we measure something n times. My question is, could we just swap the n times n case with some m, for example, m equals 2n or m equals, I don't know, n squared, and work with those cases? So that's the first question.
It depends what kind of statistical idea you have in mind. If you say the n times m comes from the experiment that you sampled n from one group and m from another group, and then measured pairwise information, then you could view it as a two-sample problem and use similar definitions and similar things hold. But if you say the m is just it's just a dimension of an individual. It's just for each individual from 1 to n, you measure an m-dimensional information. Then this would be the sequential case, where the feature space x would be to the power m. So how you use it depends on the idea, the data generating idea you have, you could say.
Žikica and Julian, my suggestion, maybe we wait for this also for the final discussion, because we're quite late on time, but hopefully we continue this. Thank you, Julian.
Okay, thank you.
Thanks a lot. And we continue now with Marija. Marija, please.
Thank you. Just a second. Okay. I will talk about univariate goodness of fit tests for randomly censored data. Actually, I will present two approaches for dealing in such conditions. First one is to adopt test proposed for complete data case, and second one is to transform the data and then to use some tests for complete data case. When we have goodness of fit testing problem, actually we have one ID sample with some distribution function f, and we want to test that this f belongs to some family f0 against complement alternative. And we can use two approaches. First one is some goodness of fit tests for based on empirical distribution function, such as Kolmogorov-Smirnov, Kramer-von Mises, or Anderson-Darling test, which can be used for different distributions. On the other hand, we can use some tailor-made tests for some particular distribution, which are based on some properties of the distribution. Especially suitable type of properties for construction of goodness of fit tests are characterizations. They are relatively simple and very suitable for construction. Actually, characterization is properties that only one particular family of distribution has. And because of that, there are a lot of different tests based on characterization. Especially suitable type of characterization for construction of goodness of fit tests are equidistributional type characterizations, which means that if we knew that two homogeneous functions which depend on m independent and identically distributed random variables are equal in distribution, then random variables has some particular distribution f0. Equality in distribution, we can interpret it in different ways as equality of distribution functions, equality of density functions, or equality of different integral transforms, such as Laplace transform or characteristic function. And because of that, based on only one characterization, we can construct a lot of different test statistics. Natural approach is to estimate mentioned functions and to consider their difference in some space. In that case, we obtain some U empirical process of order M with presented kernel, and we know in this case that the mean function of the kernel is equal to 0 under the H0. After that, test statistic is obtained as some transformation of this process, such as integral or L2 transformation. For our results, we use test based on empirical Laplace transforms, and the test statistics are obtained as integral and L2 transformation of the difference between two empirical Laplace transforms of the random variables from the characterization. Also, we use two characterizations of exponential distribution. They are relatively simple, Puri-Rubin and Dessous, and Dessous characterization we used for M equal to 2. You can see which functions are actual in the are equal in distribution here. All previously mentioned is for complete data case, but in survival analysis, sample is often limited due to some censoring mechanism. The outcome variable of interest is the time until an event occurs, actually survival time. And for some individuals, we don't know exactly the survival time. We actually know that the exact survival time is larger or less than the time which we can see in the data. For example, in some research in Kenya, researchers follow some group of baboons for 152 days. The baboons sleep on the tree. When they are hungry, they go to the go down to the ground, and the researchers define descent time as time when the medium baboon came down. In that time, half of the baboons are on the ground and half of them are on the trees. 94 days, the descent time was before the arrival of the researcher, and in that case, the researcher notes the time when he arrived, he or she, and in that case, we have randomly left censored data. Similar examples for this or other type of censoring we can find in all data-dependent research area. Because of that, there is a need for studying the goodness of fit tests for this kind of data. Although the first tests have been proposed in 20th century, until now, this field of research is still not well explored. In our research, we consider randomly right censored data. Actually, that is n pairs of the data. First argument is a minimum between two values. First one is true survival time, and second one is censoring time. And second argument is indicator of censoring, which is equal to 1 if the data is censored and equal to 0 otherwise. Also, we assume that the censoring model is independent. Actually, we consider stronger assumption that these two sequences of random variables are independent. When we have this kind of data, there are different approaches for goodness of fit testing. First one is test adaptation. That means that we adapt some tests for complete data case for this kind of data. And here are presented first three adaptation of tests. Actually, Kozil and Green adopt Kramer von Mises tests, and Akritas adopt his squared test. This is a well-known tests. Second method is data imputation, meaning that we change all censored elements with new values. There are plenty missing data imputation algorithms, but most of them are for missing at random data. Censoring is actually special kind of missingness, where missingness depends on value itself. And because of that, we need different type of imputation algorithms. We found just one data imputation algorithm for censored data proposed by Balakrishnan and co-authors in 2015. And they suggested very simple procedure based on null distribution, and I will explain it later. Other data transformation method is data imputation. Actually, that means that you excluded all censored elements from the study and conducted a test on a smaller sample. This is very popular in literature, especially in social sciences. And the last method is ignorance. Actually, in this method, you do nothing with the data. You treated all the data as uncensored and conduct original sample or original test on that data. I will explain first and second method in more details. For adaptation of tests, generally speaking, there is two approaches. First one is for tests which are functional of empirical distribution function, where this empirical distribution function is changed with Kaplan-Meier estimator. And there are some tests based on this method in literature. Other method is adaptation based on inverse probability censoring weights approach. We found just one paper with this method, and our recently proposed exponentiality tests are based on this method, and I will explain this method in more details. The idea comes from sampling with different probability of selecting elements. Actually, here, sample elements differ in the probability that they do not provide complete information. And when we scale it with the inverse probability that a sample element is not censored, we reduce the influence of censored data in the sample. This method was firstly used for dependent censored data in Cox model. In our case, we adapt our empirical process such that we have this weight function here labeled with red, and this weight function is actually product of indicator of censoring divided with survival function of the censoring variable. The good thing is that this is again empirical process, and we can use the whole theory for U processes for theoretical results. But problem is that censoring is in most cases uninformative, and we actually don't know which is the survival function of censoring variable. Because of that, we need to estimate it and replace it in the formula with estimation. Now the problem is that this it's not anymore empirical processing, and we need to obtain the theoretical results for it. In both cases, the test statistics are formed in the same way as in complete case, as integral or L2 transformation of the process. We prove the theoretical results for the process and for these two test statistics. I will not going into the detail, just to say that this process converges to some centered Gaussian process with presented covariance function. Problem here is that those assumptions can be checked only in the case of informative censoring, when the censoring distribution is known. Or we can use it in large sample case when we can estimate this covariance function. Based on this result, we obtained results for test statistic. For first one, the limiting distribution is normal distribution with obtained parameters. And for second one, the test statistic converges to linear combination of chi-squared random variables. All three theorems can be used in informative censoring model, or when the data is large. In case of small and moderate sample sizes, we need to use some resampling procedure, and we proposed one bootstrap method for simple and composite case. The difference is only in one step. First, based on available sample, we need to compute the value of test statistic. On the other hand, we need to estimate the critical value based on sequence of bootstrap test statistics. Those bootstrap test statistics are obtained based on bootstrap sample. This right censored bootstrap sample is obtained from two samples. First one from Kaplan-Meier estimator of distribution function of censoring, and second one from null distribution. Based on this estimated critical value and value of test statistic from the first step, we can make decision to reject or not to reject null hypothesis. All three steps need to be repeated large number of time, and estimated test power is percentage of rejected null hypothesis. This method is theoretically justified. For data imputation method, we consider two algorithms. I already mentioned first one. Actually, this method is the idea of this method is to replace all censored elements with new ones. These new elements are obtained as inverse of null distribution of some value from these presented intervals. When we replace all censored elements, we then have a complete data case. This algorithm, we know that this algorithm will give good sizes of tests, but when we talk about power performances, we don't know what to expect, because we don't know what is the influence of null distribution in that case. Because of that, we want to upgrade this algorithm. And instead of using null distribution, we used smooth approximation of Kaplan-Meier estimator. And all other steps are the same as previous. For a smooth approximation, we used Bezier estimator proposed by Kim and co-authors in 2003. And based on this whole what I said, we conduct one empirical study for moderate sample sizes and significant level 5%. We use these 5 methods: adaptation to imputation algorithms, amputation, and ignorance procedure. We tested simple and composite hypothesis of exponentiality when the censoring rate is 10, 20, or 30%. Of course, we suppose that censoring method is uninformative, but we need to obtain the rate of censoring in the starting sample with some method. And for that, we use Kozel-Green model and sensor modeled with Lindley distribution. In both cases, parameters of distribution are obtained such that produced certain censoring rate. We consider 7 test statistics. 4 of them are our test statistics, and 15 alternative distributions. For competitor tests, we consider these 3 tests. Here are presented their adaptation for randomly right censored data. First one is Kramer-von Mises test. Second is test based on maximal correlation. And the last one is test based on properties of decreasing mean time to failure class of life distribution. We can notice that first and second tests are based on Kaplan-Meier approach. And the last one is based on inverse probability censoring weight approach, similar as our method. First, we obtain the empirical sizes. With bars are presented the empirical sizes for causal when the censoring model is causal green, and with these small squares are presented the sizes when the censoring is Lindley distribution. We can notice that the sizes for imputation algorithm 2 are larger than 5%. Before I proceed to the solution for this problem, I will say that for other methods, we can see that the results are very similar to the 5. When the percentage of censoring is 10%, the difference between values when the different censoring mechanisms are used is not significant, but when the censoring rate increasing to 30%, that difference is noticeable. For imputation procedure 2, we proposed a calibration method, which means that instead of using significant level of 5%, we found one calibration value which produced for each test statistic test size equal to 5, and then power performances are obtained for those calibration levels. We can see that for a different censoring mechanism, those values are very similar, and that the impact of censoring distribution is not significant to the calibration. Because of the time, I will skip those results, empirical powers. I will go to the conclusions. If we compare tests between each other, we saw that most powerful tests, except for one alternative, are new tests based on U empirical Laplace transforms. If we compare for different censoring rate, those methods, we saw that for the censoring rate 10%, the adaptation and the novel imputation algorithm are not sensitive to the censoring distribution, while for other data transformation approaches, that is not the case. For all considered approaches, the impact of the censoring distribution is noticeable for larger censoring rate, but the conclusions stay unchanged. The power of proposed test is not much affected by the change in the censoring level. And if we compare the methods, imputation algorithm 1 have always smaller value than adaptation procedure. And the impact of the censoring distribution can be significant in this case. Imputation algorithm 2 needs to be performed with the calibration, but the results after calibration are more stable than for other procedures, and this method is computationally much more convenient than the adaptation procedure. If we consider adaptation and ignoring, they are well calibrated only in composite case. For some alternative distribution, they give good results, but for some, the results are not well. And here are some references for my talk. Thank you.
Thank you. Thanks a lot. Great. Any question? Congratulations on the presentation. A very short one, and then maybe we continue and have discussion afterwards. Have you considered also left censoring? Would it be possible? Probably this holds for right censoring, right?
Yeah, yes. We didn't consider, but it would be very similar.
Okay. With the same distribution and symptotics and.
Yes.
Okay.
Yeah.
Okay. Okay. Thank you. Thanks. Let's move also forward now to Charles Pretorius for the final presentation.
Thank you, Andre. Can you see the screen?
Yes, maybe to put it full screen.
Yeah, it's fine like that.
Yes.
Okay, so thank you for organizing this session, Andre and Bojana, and thanks for the opportunity to talk about some of my work. So the talk will be on goodness of fit tests for alpha stable distributions, and at the end I'll give you some application to gauge models, multivariate gauge models. So first of all, you all know that a random vector has an elliptical symmetric alpha stable law. If you can write the characteristic function like this, in this form where Q is a dispersion matrix and delta is some location vector. And the topic of the talk, or the problem, is to test for a random sample of observations x1 to xn, whether these observations are observations from an alpha stable distribution, okay, for some values of some of Q and delta. So of course, special cases of the stable distribution are the Gaussian distribution when alpha is equal to 2, and the Cauchy distribution when you choose alpha equal to 1. So equivalently, we can restate the hypothesis like this, where if we standardize the vectors x with an appropriate Q and delta, then we get sort of standardized observations, and we want to test whether they come from a distribution with this characteristic function. Okay. So of course we don't observe Q and we don't observe delta, and these need to be estimated from data. And then I'll say something about how we estimate these quantities later. So, but all our tests are based on these standardized quantities, which I denote by y hat. So our test is an old idea. It's based on this L2 type statistic where we compare the empirical characteristic function calculated from these standard observations to the hypothesized characteristic function. Yeah, so of course, if these two are close to each other, then we would expect this test statistic to be small, and we would not reject the null hypothesis. Otherwise, we would reject it. Okay, so as is usual in these type of statistics, if you do some by simple algebra, you can see that the statistic can be written as a function of these three integrals: IW, KW, and JW. Now, the first integral here, IW, is a familiar integral, and if you choose this W spherically symmetric density, you see this is exactly the characteristic function of a random variable with this density. So if you choose W a symmetric density, this is usually easy to calculate, this IW. A little bit more complicated are these two other integrals, KW and JW, which also has this factor in there, this extra factor. Okay, so if we can evaluate these integrals, then we can easily evaluate the test statistic. So as I just said, the IW, if you choose a spherical density, then what it boils down to is just evaluating a real valued function, a univariate function, which depends on this Euclidean norm of the argument x. Okay, now we start off somewhat generally, and we choose this weight function, which is proportional to the density of spherical Cox type distributions, and it depends on two parameters, nu and r, and of course, then this statistic or this integral that you want to calculate is just simply that statistic. So the next slide, I don't want to talk about too much about the next slide, but in general, for different values of x and mu and r, you can find either closed form expressions for that integral, or you can find series expansions, which you can probably approximate by chopping off chopping it off after a number of terms. But we have tried this, and we still have some problems in the implementation, because some of these series with problems with getting them to converge numerically. There are some numerical issues. So this is just to show you that in general you can using the characteristic function of the spherical cost type distribution, you can get these expressions for those integrals. Okay, so to simplify things further, we choose nu. So in this weight function, we choose nu equal to 0. So we end up having this function there, that weight function. And if you look at that weight of that function, you see it's just the characteristic function of an alpha 0 stable distribution. Okay, so if you use an inverse Fourier transform, you can recover, because it's symmetric, you can recover the density from the characteristic function. Okay, so this formula gives you some way of evaluating the density function of an alpha stable random variable. And if you use this expression, you can write that integral with this weight function, one of the integral that you want to evaluate in the test statistic, with this weight function as a function of the spherical alpha stable density. Okay, which is nice. Because this should be easy to evaluate, and then the test statistic can be calculated like this. It's just a function of this multivariate stable density. So nowadays there are many procedures to numerically evaluate F alpha in more than one dimension, and there are several possibilities. Fast Fourier transform, or what I like to use in this work is this fact, which comes from a paper by one of the co-authors, John Nolan, which because the alpha stable density is spherical, you can write it as a function of a univariate density, the density of what he calls the amplitude of x, which is just the Euclidean norm of the alpha stable random variable. So instead of evaluating a multivariate function, you can evaluate that function as a univariate function, and there are several integral expressions for this quantity. So what we do in the simulations is, because this is a univariate function, we can calculate it before all the simulations ahead of time for different values of this argument, and then create a lookup table to easily evaluate the density. Okay, so how do we obtain critical values for the test? So we make use of this fact that if you use location scale equivariant estimators, that is estimators which satisfy these equations. So you can if you shift the data and scale it by a matrix A and a vector B, it just means you can shift and scale the location vector, and you can scale the dispersion matrix. Then if you look at the test statistic, you see that the value of the test statistic remains unchanged. So this means that the test statistic, the null distribution of the test statistic, which we need to get the critical values for the test, don't depend on the estimators, or actually the true value of the true values of the dispersion matrix and location matrix. So we can just get the critical values using Monte Carlo simulation by choosing delta equal to 0 and the dispersion matrix, the identity matrix. Okay, so there are several ways of estimating delta and Q. You can use an empirical characteristic function estimators, or one of the co-authors suggested projection estimators. But because we want these properties to hold, we make use of the maximum likelihood estimators. And of course, to calculate them, we need to evaluate this spherical density as well, which is numerically intensive. But as I said earlier, we nowadays it's fairly easy to do that. Yes, and this is just how we choose the initial values. This is not so important, but for this optimization problem, we first use projection estimators to get the initial values for this optimization problem. Now, we have some asymptotic results. We don't have the limit null distribution yet, so that's still work in progress. But what we can say is, in general, if we assume that our estimators, given some, well, any underlying distribution of their observations, if they converge to some values, then we can show that the statistic divided by n converges to this quantity, and this, what you see in the middle, between the modulus, will be 0 only under the null hypothesis. Otherwise, this quantity will be positive. We'll have a positive quantity on the right-hand side, so the test D and W will be consistent under alternatives. Now, that was for the symmetric case. Now, recently we've also been looking at the asymmetric case, and in the general case, you can, when you have a random vector, which is an alpha stable distribution, you can, well, it has an alpha stable distribution if you can find a spectral measure gamma and a location vector delta, so that you can write the expected the characteristic function, the true characteristic function of the random variable like this, e to the power minus some integral, depending on that spectral measure, plus this location, well, some function of this location vector. And there is a reference by one of the co-authors, Panoshka and McCulloch, on this definition. So more generally than other hypothesis, we would like to test whether sequences of observations come from a multivariate alpha stable distribution. Now, the problems we had before, as I explained, those tests depend on calculating the density of an alpha stable random variable or multivariate alpha stable random variable. So of course, in this case, it will be even more complicated. So what we do is we use a recent idea by, the references on the next slide. I'll give it in a while. So what we do is we again use the empirical characteristic function, but now we compare it to also an empirical characteristic function, but of data, artificial data generated under the null hypothesis. So xj is as before, the original data, and x0j are observations generated under the null hypothesis, and I'll get back to how we do that in a bit. Now again, you can write the test statistic as a double sum of a function of an integral, where this integral IW is the one, and you saw earlier, which of course, if you choose a spherical density, you get a nice real valued function. Psi, which puts the statistic in a nice calculable form like this. And then we don't need to calculate the density or the characteristic function anymore. This is easy to evaluate. Now, there's the reference of this type of statistic. Now, there are some, well, first of all, in this paper, they show the asymptotic validity of such a test under some conditions. And secondly, they also address some practical issues, like it's obvious, of course, if you calculate this statistic, every time you do it, since these observations, artificial data is generated every time, you'll get a different value of the test statistic. So they propose doing this 30 or 40 times and taking the mean of all the statistics or the maximum or something like that. But there's the reference if you are interested. So, well, one thing I mentioned earlier is we need to generate observations under the null hypothesis. And to do that, and to simplify things, we assume that that spectral measure, gamma, can be approximated using a discrete spectral measure. And this approximations like these have been formalized, and conditions for that have been given, and also how large you should choose this discretization, and which mass points you should choose to get a good approximation, and there's a reference for that. So we follow this approximation. Well, we use a discrete measure, and then we estimate these weights, and this location vector delta, as explained in this paper, which is quite a procedure, but no, I won't go into it. There's the reference, and once you do that, you can generate an observation under the null hypothesis, which satisfies the null hypothesis if you generate an observation according to this expression here. Okay, where gamma hat are these estimated weights from the discrete spectral measure, and delta hat is the estimated location vector, and zk's are just univariate random variables, well, totally skewed to the right, univariate random variables. And you can also do it for the case alpha 0 equal to 1, but I'm not showing it on the slide. So this x0 will have an alpha stable random distribution. Okay, now some simulation results. So first, the symmetric case. We considered the 4-dimensional, 6-dimensional cases, and we considered alternatives from isotropic or symmetric alpha stable distributions, and also from skew Cauchy distributions. And we compare our results with this test, which is from a 2015 paper by Simos-Mentanes, and it's based on this characterization that X is symmetric alpha stable if and only if the characteristic function to the power alpha is equal to the characteristic function evaluated in the point A to the power 1 over alpha t. Yes, okay, so our significance level is 10%. So here are some results where I took the null hypothesis to be with stability index 1.9. And as you can see, as you move away from the null hypothesis to heavier tail distributions, alpha equals to 1.8, 1.7, 1.5, you can see that the power of the test increases, as you would expect. And it also compares well to the existing tests which are given here. And also, as the sample size increases, you can see that the power of the test also increases. A problem that we have is that for lighter tail distributions and for smaller sample sizes like this sample size 50, we get this under rejection issue. You can also see it in the null hypothesis as when we test for alpha stable distributions with stability index 1.8, you see this sort of under rejection error for smaller sample sizes. Okay, other than that, what I said on the previous slide, it also holds here, larger sample sizes and further more away from the null hypothesis, the power seems to increase. I'm not going to talk about all these tables. This is for skew alternatives, and you can see you also have a competitive power with existing tests. I just would like to say something about the under rejection issue that we have. This is also reported in this paper by Matsui and Takamura, where they have a similar empirical characteristic function-based test for the univariate case. And to get around that, one solution is to choose. You can also see from the results that the power and the size depends heavily on this tuning parameter in the test. That appears in the weight function. So you can choose that R that maximizes the bootstrap power. It's an idea by Tenreiro. But if you apply directly, it doesn't work that well because we have heavy tail data. So we use this idea of Cornea, Madeira, and Davidson, who proposed the bootstrap for heavy tail data. So I'm not going to go into this. I spoke about this in another talk. So the general asymmetric case. So for this case, we generated observations from an alpha stable distribution with discrete spectral measure with 5 mass points on the unit sphere. And we chose these weights, these gammas, and these mass points on the unit sphere. If you plot that density, it looks like this, and these are the the level plot or the contour plots, level curves. You can see clearly it's an asymmetric distribution. And to estimate that discrete spectral measure, of course, in practice, you won't know where, which distribution generated the observations. So we just chose 10 mass points, and according to this, and the locations of the mass points according to this paper, and estimated the gammas according to their procedure. And then to get the critical values, we applied a usual standard parametric bootstrap. And the results look quite good. You can see that under the null hypothesis, so here we have the null hypothesis here is a stability index of 1.9, and you can see in that case the levels are reasonably respected quite well. And then under alternatives, there's power, except for the lighter tail distributions. We have again this issue of lower power, but this seems to disappear if you look at this table. For larger sample sizes, the null hypothesis here is stability index of 1.8. You see that it seems to disappear for larger samples. Here's just another example where the stability index is 1.5, and it looks quite okay. And I just also want to mention, we don't know of any other tests that test for alpha stable distributions in general. Sorry, do I still have a minute or so, Andre? Or?
Yes, maybe 1 minute, 3 minutes.
Okay, so I'm just going to go through this quickly. I'm not going to talk about the details. This is just to show that we applied the model to gauge models where we have observations from a gauge, a certain multivariate gauge model, and specifically this constant conditional correlation model proposed by these authors. And we have these observations, and then we fit this model, estimate the parameters. So there's just the choices we made in the simulations. We estimate the parameters to recover the residuals, and then, of course, run the test. Sorry, we apply the test to these residuals obtained from the model fit to see whether they come from a multivariate stable distribution, which we, of course, in the simulations generated from either a stable distribution or not. And in the Monte Carlo results, you see the same thing, that the test respects the level and it has power under alternatives. Okay, so this is just one type of multivariate gauge model, but we intend to consider other type of multivariate gauge models as well. Thank you.
Hey, thank you. Thanks a lot as well. Also, due to time reasons, I suggest we skip now to discussion and leave the questions for the follow-up debate. Great, thanks. Bojana.
Okay. First of all, I would like to thank you for very interesting talks. What is common for all talks is that all participants discuss some model specification tests, obviously, but from rather different setups, which are in some sense connected if you go to it deeply. So we can see during Tom's talk that the notion of differential privacy is nowadays very hot topic. And I actually have seen for the third time in my life that very rigorous framework for differential policy. But from my point of view, it's rather interesting due to nowadays constraints with data, with sensitive data, and there are plenty of sensitive data. And usually we are interested in testing some hypotheses for this kind of data. So this was very interesting for me. And I would like to ask Tom, what is known for some other tests? So this approach reminds me at the first sight on error measurement model, because you are introducing some randomization. So I would like to discuss with you what are the differences with the measurement model, and with that connection, what is the possibility to introduce this randomization in some other test? From my point of view, it looks quite natural to add some noise and to apply tests on the privatized data and to see what is going to happen with null distributions of test statistics, alternative ones. So it sounds to me rather feasible. And when I was looking what has been published, I didn't see many results about that topic. So I would like to ask you what is known for other tests, not just the separation rates for some classical tests you presented.
Yeah, thanks. There has been some work on other tests. I think people have done work on independence testing, for example, but
most are focused on the error separation rates and quality of the tests. So yes,
yeah. So I think that there is lots of scope to do work on testing in privacy. A lot of the work that exists is done in kind of computer science literature, and those are the kind of results that they tend to prove, these kind of separation rates. But in the statistical literature, the statistical literature on differential privacy is relatively small, and so I think it's there's definitely a lot of room to make contributions there. With the relationship with error in measurement models, I think that's an interesting thing to think about. I guess a difference maybe is that in privacy, you're allowed to choose the error distribution yourself. So you can choose what kind of measurement error you have in order to design the best possible test. So I'm not super familiar with the measurement error literature, but I understand that usually the noise distribution it's not something you choose, right? It's kind of imposed. And in privacy, it's different because you're allowed to choose it yourself.
But what if you are the third party, in a sense that you get already privatized data? Mm-hmm. So you don't know what was the mechanism. Okay, you can assume that is the Laplace one because it is the most commonly one used, but what if you don't know that? So
yeah,
it is in connection with the error measurement model. So the problem with unknown errors is something not explored. That's why I'm asking you that.
Yeah, certainly. Yeah.
So I didn't notice any real data example. So
no,
I have to ask myself, you know what I should do when I got the information that the data is privatized and I want to test. So
yeah, so usually the data analyst would choose the mechanism themselves. Yeah, you're right. We haven't done any real data examples. Unfortunately, the performance, you tend to need quite a lot of data to get good performance with privatized algorithms. They do require a lot of data, and the rates are much slower than the classical counterparts. So I think people typically tend to work on theory and occasionally have simulations because the empirical results are not always that impressive. Yeah, in principle, people are giving algorithms, but they do tend to require quite a lot of data.
And how you will privatize the sensor data, for example. It's a survival unit, so it's a kind of sensitive data. So
sure.
how you would do that?
Well, it depends on what kind of data it is. I suppose if it's continuous data, then the most common kind of mechanism it would be a Laplace mechanism that you mentioned earlier.
Mm-hmm.
One kind of drawback of local differential privacy is it tends to require data to be bounded, or it works best when data is bounded. So you might have to kind of truncate your data first if it was unbounded before adding noise. The most common thing to do would be to add Laplace noise. But if your data takes values in some large set, then you might have better performance with more sophisticated algorithms. So we, in our paper that we wrote on robustness, we also considered a mean estimation problem. And we found that if the set of allowable means is very large, then you can do better than the Laplace mechanism. So then you have to design a more sophisticated algorithm in that case. But if you have simple data that takes values on a small set, then Laplace mechanism is pretty good.
Okay, thanks. And what do you think, is it possible also to use the same mechanism to privatize the relation matrices or something like that?
It's a good question. These kind of models, you have to think more carefully about what it means to be private. In most private algorithms are designed for this kind of sequential setting when each data point applies to a single individual, and then it's kind of clear what it means to protect the privacy of the individual. You just have to randomize that data point. What gets more difficult is when the observations, you can have multiple observations from a single individual, as is the case with these relational data sets. So if I understand correctly, there you have a matrix where an entire row kind of resamples an individual multiple times. And so you have to think a bit more carefully about what it means, what is an individual in that setting. And also it's difficult because each data point corresponds to two people. And so you have to think carefully when one person releases a privatized view of that data, they're also kind of affecting the other person as well. So,
yes, but it's looked like it's rather challenging, but very important.
Yeah, no.
Because information that you're following the person on Facebook, it's quite important information for a unit. So
yes,
maybe it would be interesting. Thanks. And
definitely.
with connection with that question, I would like to ask Julian, are there any previous results for relational matrices? So you proved quite general settings, introduce it and prove some general results. But usually when you want to apply the general result to the concrete one, it's not so easy. So I wondered whether there are results for the relational matrices known so far, known before.
Yes, I think the result for the YoungStatS convergence for the matrix setting I presented, it's known for a long time. I think it's from Kallenberg, I think, from maybe 20, 30 years ago or so.
Are those results used in goodness of fit testing on matrices or relation distributions
for the
or
application?
something like? Yes.
Oh, I don't know if the results have been applied in this direction. I don't know. Maybe for I presented this array example, this symmetric array, because you can make nice pictures. So maybe another example I could have chosen would be exchangeable random graphs, which are undirected. So there, the array data would have been just, if you plot it as a matrix, just an upper triangle matrix or symmetric. I think this for exchangeable random graphs, there are for sure there are some hypothesis testing research.
Thanks. And also I wondered when I heard Charles' talk, whether it is possible to add, to use those results, to extend it to the time order data, like time series. Are those objects known so far? Usually there is a technique how you can proceed from the IID to time series data, and it is well known. It's complicated, but well known. So I wondered whether are there any such objects time ordered?
So in the sense of time series data, in the sense of stationary processes, or
something like that. For example, at each time unit, you have a relation matrix about who is following who on the social networks or something like that. So you would want to consider that random process?
Maybe in continuous time, yes, I think it's a combination of continuous time process and exchangeable random objects, for example, appears in coalescent theory. In biology, this Kingman coalescent example. Basically, there you have such a phenomenon where you have a continuous time process where at each time the value is an exchangeable partition. And as time progresses, the blocks of the exchangeable partition coalesce together until finally they will be just one block. So there's there is some theory for continuous time processes with this connected to exchangeability. For example, you could this general abstract framework, you could use it to model this the state space also for this. You could introduce continuous time at that point, but I don't know if it's possible to make general theory in this direction.
But how did you come to idea to work on that general object? Usually, you're starting from the bottom of the pyramids and go up. So
yes, I studied several examples of data structures and certain connections which were not so clear for me, and then I asked what was the common thing that happened there, and then I searched for definition that captures all, and over the time it showed that it's just a functor that you need this abstract definition, and then you can recover the examples I started with.
Very interesting indeed. I think that the tools you provided to methodological statisticians are quite useful to the whole community. Okay, thank you. And also, I have few questions for Charles. I'm not following the order because in some sense, the questions are in some sense related. So I would like to, that's why I'm not asking you by the order you presented. So I wondered, are there any constraints about the stability parameter? In a sense that it makes the fact that, for example, alpha is rather small makes problems with simulations, or some distributional property doesn't work. So I didn't notice any constraints on your slides, but I wondered, are there any? Because this parameter is quite important for the estimator properties.
Yeah. So you will see in the simulations that we only went down to 1.5, and I have other simulations down to 1, alpha equal to 1. But even in those cases we have some issues, as I pointed out, and it gets worse as alpha goes closer to 0. So theoretically, I can't say anything because we don't have theoretical results yet in null distribution and those types of things. But numerically, it is challenging in some cases. So you'll see that's also the cases that I presented are for stability indices closer to 2, 1.6, 1.5. So, and we already have some issues there.
But for example, for the properties of the estimators, you mentioned that you use some specific bootstrap for heavy-tailed observations. So what is the key point with that bootstrap? Why this bootstrap is different than the typical one for used in those cases?
So do you mean the choosing that parameter?
You emphasize that you use the bootstrap for heavy-tailed observations. So I wondered what is the crucial difference between the typical parametric bootstrap and that one?
So that is a parametric type of bootstrap. So you estimate the stability index and skewness parameter, and then you sample observations from a alpha stable distribution. So it is a parametric bootstrap, and we only use it in that case to choose that tuning parameter which maximizes the power, because the usual bootstrap doesn't seem to work there. So you need to use a parametric bootstrap.
Yes, I understand that, but why this one is different than all others? So are there any constraint on the value of alpha in that bootstrap, maybe?
Yeah, so that I can't say. I don't know. I don't know. Yeah.
Okay. And also one question that comes to my mind, did you also consider the application on the cryptocurrency market due to high volatility of the observations?
No, but that's a good suggestion. We still need to get to
a real data example, so
yes,
maybe.
Yes, yeah. So maybe that's a good suggestion. Thanks. No. Yeah, you see, there's some bothersome issues in the numerical work. So.
And there are plenty of issues when you're working with those kind of time series, but yes. I just wondered, is alpha the main reason why some things doesn't work or not? Yes, and for the end, I left Marija because most of her work is our joint work, so I don't have anything to ask her, but maybe I can say a few words and make it a connection with the previous talks. In some sense, now it comes to my mind because we concluded during our work that imputation is maybe a better way to proceed, maybe not so methodologically correct always and theoretically justified, but quite easier and more natural, more applicable, more general. So it comes to my mind, and that is also a question for Tom and Marija, whether this imputation also does a kind of anonymization, because when you don't have a data, when you have a missing units in the data and you imputed it using some stochastic algorithm, are you privatize your data enough? What do you think?
Possibly, yeah. I guess
maybe that would be a good way to proceed with the anonymization, just to remove few units and to impute data.
Yeah, so I guess you'd be privatizing some of the data, but not all of it.
Yes,
it's a bit different to the usual setup, but yeah, it could definitely still be interesting.
Yes, it just come to my mind. Marija, do you have to add something? What do you think?
I don't know. Maybe we can think about that.
It's quite interesting. Actually, those talks were rather stimulative for the connection of different areas. We tried our imputation algorithms in several setups, and it works. We didn't justify it all, but it works. It's important to work for the beginning, so maybe it would be a good way to proceed. Who knows that? I don't have any questions for now. So, are there any questions from the audience?
Thanks. Yes, thank you, everybody. Please, anybody in the audience, open up and also ask questions. We just had one very recent applause. I would say thank you all. Very organized. Questions. Just unmute. Maybe Žikica we had, but also naturally others. I see.
Yes, hello. Hi, everyone. And thank you for the presentation. Thank you for the presentations. I just wanted to say thank you. I don't really have a particular question, but very nice presentations. And I enjoy the different thinking on each application and each statistical methodology. Thank you again.
I would have one question for all. It's a more general question. There could be others, but in terms of model specification, today we know that we deal with machine learning, we deal with rapid advances in data modeling, in many mathematical advances. What is the future here? Tom presented local differential privacy. Likely we would need additional seminar probably just for this topic to address it. But are there any special issues that you see, say today in particular in terms of data science arising and similar issues for the future of model specification? What to be careful about, what to develop, are existing testing procedures sufficient, and are there any developments for future which would need to be followed maybe?
Yes, I think model specification is important. I think this is what I observed as well. I mean, each application is very good and well thought, and it has a good statistical background. But yes, from the econometrics point of view, I would say maybe I'm probably there is a gap between the two, connecting the two. Yes, but yeah, I think it has definitely with machine learning. The future, yes, connecting these two areas.
Thank you. Thanks. Maybe also the speakers and
maybe if nobody wants to add anything else, it's rather good question, postulated always during the students' lectures. What is the gap and what is the difference between statistical machine learning? What we should do next? And I would say that the main difference is what we want to achieve, in a sense that the model specification tests are quite important, but maybe they are not enough exploited for some specific machine learning tasks, in a sense that maybe they are not, for example, the distribution of some feature or something like that is not already yet exploited as an input for some classifier or something like that. And I think that there is a future. For example, if you want to keep the topological structure of the data, you don't care about the distribution of some topological data analysis feature distributions like those diagrams or etc. You are not taking into account that those points and those features, those summarized statistics are the random ones. So you are not taking into account the whole distribution. And I think that there lies a really nice space for the future considerations to take into account the stochastic nature of the output of some algorithms and the input as well. So that's what I would like to say on that topic.
Maybe also anyone else. It's a very general question.
What would be your opinion about that?
You mean my own and
your own opinion? You're the moderator of this very good YoungStatS webinar. You heard plenty of ideas, some from machine learning, some from econometrics, some from methodological statistics. So what would be your conclusion?
It's naturally, related topic, but I would say a little bit different. Naturally, so from the debates that I know, say in econometrics, there were quite debates between Josh Angris, the Guido Imbels, and Isaiah Andrews in the interviews. So there are debates a lot, in particular in econometrics, about whether ML, whether machine learning really brings benefits. Econometricians are still skeptical. So in this line, it seems that indeed some things change, say the asymptotics and so on becomes on very different grounds. Currently it is either undeveloped or on very different terms, very different foundations. So naturally for model specification tests, I'm not that immersed naturally, but I assume that asymptotics is naturally essential. So you need to know how do the tests perform. So in this line, yeah, I think that it will be really interesting in the future. What will those novel approaches, also with novel likely types of data, and that were partly mentioned here, bring in terms of more classical statistical approaches, which partly relate to, I think, some of what we presented today. I think that Charles, you presented a model which could be called econometric, naturally, engarge, and so on. So all of these combinations, yeah, I think that the future will be really interesting. As you know, we discussed the IMS previously, Institute of Mathematical Statistics. There will be a conference in Florence about data science, the first one to explore more, I think, mathematical aspects next month. Yeah, I'm not a competent one, but it's a question that appears constantly. When we also discuss with econometricians, with older ones, it's all around what data science brings, what will change, and extreme diversity of spectrum. Just something.
Maybe it's just bring the answer what is going to happen, but not why. So maybe that's why there are so many econometricians that are opposed, but maybe some of them are opposed because they are not familiar with new methods. So I would say that the best way to proceed is to cooperate with each other and to try to make this gap smaller as possible. There will always be a gap, I think so, but we should do our best to impute the missing points that is missing in our puzzle. So people should cooperate, not just say that something else doesn't work or not.
As you clearly pointed today, and I think in all presentations, so many different types of data, it's extremely interesting to explore from, I would say, also mathematical perspectives and their properties.
Yes, and it's just beautiful how those things works. Similarly, how these intuitions can work in other settings. So that's why I asked Julian about some concrete examples, but I'm pretty sure that his objects can be also make more generalized in order to cover even more objects. But anyway, it's a story for some of next workshops.
Anything further? Any further question? There'll be a lot of others. Maybe I also ask, when we mention this engarge approach that Charles mentioned, is there any other model that would be directly applicable related to alpha stable distributions that you discussed at the end? That Bojana, you mentioned cryptocurrencies and so on. Is there any other? And is this also related? People talk about stable diffusions. Is this related? And could this be applied also here? Maybe?
Should I answer the question? I think it can be. It's for sure, but I will just give my opinion, and I would like to hear what Charles think about it. I would say that it can be applied, but working with diffusions and residuals of diffusions as initial setup for the model specification test is not so straightforward as it is the case with some time series. So it would not be nice to say that all those things can be generalized, but there are for some diffusions that are quite used in modeling some natural phenomena, so it's worth to consider that. And what I would also like to add that the bootstrap methods doesn't work there well, at least the traditional ones, so I'm looking forward to hear more about that. Maybe you can organize a webinar on that topic. So, Charles, what do you think about it?
Yeah, so I don't know how you would do it for the fusion processes, of course. So in the discrete time series case, it's get the residuals, whatever. But yeah, it could certainly be interesting to look at it. But no.
It also depends on the discretization procedure and too many things. So
yes, I mean, already there's so many things we need to choose already, you know, in these procedures that I presented.
Maybe one should start with the classical diffusions with Gaussian noise, not the alpha stable one.
Yeah.
Okay. Is there anything further? I think it is just for the end to also mention, we discussed naturally support for the seminars for the YoungStatS that we are discussing, also some interviews in future possible publications of our supporters, and maybe some topics that we discussed today could be interesting to open in some short interview, either say in some bulletins or similar. I suggest we discuss this naturally also later, because those topics are very relevant for statisticians and others that we mentioned. Okay, thank you at this point. I thank again greatly to all the great four speakers, to Bojana naturally for excellently structured and so on discussion that was also noted, to all the participants who lasted also until the end. The webinar will be accessible in a few minutes' time. We are still in agreements for December's webinar, but it seems with anti-nulls, we will prepare the webinar on random matrices, so probability and even mathematical physics will be there. We are also, there will be webinars on Stein method and Coppolas very, very soon in the next month. Thank you to all again, and hoping to stay in touch to see you on conferences very soon.
Thank you. Keep us posted.
Great. Thank you.
Bye-bye.
Thanks.